now that we have established vector multiplication of a vector with a scalar and adding two vectors, I think now we have enough tools to cover the linear combination. Linear combination corresponds to combining two vectors or two or more vectors by scaling them and adding them. As simple as that. But let me go forward with some more mathematical definition. So like when we are, let me open up my notes. All right, linear combination. So first of all, we mentioned that during the scalar multiplication, if I have an x vector of some dimensionality, of some size, and if I multiply this x and I get some other vector y, I know the size of y is going to be the same thing as the size of x, because I am just multiplying every element of x with a, right? So that's one. I know the size of the size of a will have to be equal to size of, not size of a, size of x will be equal to, be guaranteed to be size of y. And similarly, if I were to add x plus some y and get z at the output, I know, like we covered previously, we're doing nothing but like adding each and every one of the elements. So it goes without saying, in order for me to be able to add x and y, the size of x must be the same thing as size of y, which gives a vector that's the same size of them, right? I will get size of z. So these are the essential rules, like that goes without saying, but I thought that I should say. So I can, in theory, multiply x, let's call this a1 and x1, and I multiply x2 with some a2, and I could multiply some x3, some other vector with the same size, with a3, and I can keep on doing this forever until some n, capital N of them, and multiply this x of n with that, and I can get y. So this y vector will have the same size of each and every one of these x's. And this operation, my dear friends, so this thing that I described here, let's see, it is going to take, all right, perfect. So this thing is defined as a linear combination of x1, x2, x3, yada yada yada, x of n. All right, I'm gonna start being lazy and stop drawing the x bars, underscore bars. We know here that x's are vectors and a's are scalars, unless I, like next time I come here and warn you that's not the case. So that's nothing but this is just a linear combination. I'm linearly combining 2-3 of these things. So far you might not see the importance of this, what is this doing, but it is going to come into importance. But while I'm here, I would like to define some other thing, another topic that I'm gonna call linear independence. So linearly independent set of vectors. So note that this is different from statistical independence. So like you will probably hear a lot statistical independence, like without saying linear or statistical. When you hear just x and y are independent, Most probably they are talking about statistical independence, but we have a concept of linear independence. So in linear independence, if I have some a1 times x1, a2 times x2, yada yada yada, I add all of them for a set of vectors a n x of n. I'm getting their linear combination, and all of a sudden I'm getting 0, right? So they add up to each other, and now I'm gonna draw underscore this because so this is just not the 0 number. Note from previous lecture, this is a vector of zeros, right? Everything is 0. So if I'm having this and these guys x's are non-zero, right? So if this is happening, either all of the a's, a1 is equal to a2 is equal to a3 is equal to blah 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 blah, all of these a's, they are all 0, which is 0 number, so that's 0, or since a's can be anything, any scalar, I can get some of them to the other side, right? Like I can take one of them. Let's say, so either this, or I can write a1x1 plus a2x2 plus yada 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 all the way to a n minus 1 x n minus 1 is going to give me a n x n. So it means that I can get one of them, x of n, by linearly combining others, right? Do you all see that? The second case scenario suggests that, like, if I linearly combine with some a's n of the vectors and I get 0, it can either mean all of the a's are 0, or I can combine all but one and get the last one from a linear combination of others. So if the second one is happening, if this is the case, I can call x1, x2, x3, yada yada, x of n are not linearly independent, right? So what does this mean? I can get one of them via linearly combining others. So it makes them linearly dependent. One of them depends on others linearly. If this is the case, this is the only way that you can get the summation. It means they are linearly not dependent, independent. Whoops. P. Independent. All right, now let's go ahead and open up some visuals to comprehend this better. Let me transition to this. So linear combination. What are we doing when we are linearly combining this blue and red, x and y? What I'm doing, I'm multiplying x with a and multiplying b with y, and they're just linear scalars, and I'm getting a summation, right? So like this linear combination for a equals -1, b equals -1 is going to give me one vector. So note that by linearly combining these two guys, I will change a and b. As I change a and b with different numbers, I will get different yellow things, right? So the linear combination of these two guys is going to give me, by guys I mean the blue vector and the red vector, x and y, is going to give me the yellow. So any of these yellows can be obtained by linear combination of x and y. So that's what linear combination is doing. Why is this important? It is going to become important when we understand linear independence. As I mentioned before, a set of vectors, these are called linearly independent if and only if. If and only if means the first condition implies the other, and the second condition implies the first one. So if and only if all of the C1s are 0. I wrote in my notes A's, but doesn't matter, like it's another letter for describing the scalar. So if the if it is the only condition for them to yield a 0 vector by linearly combining, I can call them linearly independent. So what does this mean? Let's look at one example. I have 3 vectors here, and it's not directly visible, but the third vector can be obtained from the first 2 vectors, so that it makes them linearly dependent. So if I can multiply x1 with -2 plus x2, I get x3. So this is the thing. So although I have 3-dimensional vectors, and 3-dimensional vectors can live, now I'm going to introduce some abstract topics, can live on 3-dimensional spaces, their linear combination, they all, well, maybe I should state like this, their linear combination, the linear combination of the first 2 is going to give the third one, and this is going to imply in a second that these 3 vectors actually do not live on a 3-dimensional space. So I will discuss this in the next video for the sake of keeping this video short as promised. But the next video I will discuss the geometric interpretation of linear independence.